Hi, everyone. Welcome. We are letting everyone in from the waiting room, and we'll just give it a couple more minutes here before we launch and kick off. I'll start by just sharing some of our sponsor slides and then kick it over to Dr. Alba. Everyone should be muted, but feel free to mute yourself if you uncheck it and use the chat and Q&A feature in the Zoom call. We'll preserve enough time at the end to answer some Q&A.
One quick note before we get started, if your Zoom screen name does not match the name you registered for this with, and you would like a CEU, please click the three dots in the bottom corner of your picture, click rename, and rename your Zoom name to match so that at the halfway mark, when we go to do our attendance for CEUs, that we can make sure everybody gets matched up.
Great. Well, I'd say we're 2 minutes in and let's get started. I'll first just acknowledge our group. So we're the AIA Chicago Committee on the Environment with a 2030 commitment and knowledge community here, local chapter in Chicago. We do have some members also as part of our national group, like Daniel. And then a big thanks to all of our sponsors. We'll start with the champions of the knowledge community and affinity groups, Canon Design, McNichols, and then friends of the Casey sponsors. American Institute of Steel, Bricks Incorporated, which is, I think, has a great salvage options as well. Maypie, Premier Brick, Sierra Pacific Windows. And our 2025 supporter level sponsors, Klein and Hoffman and Rockwool. Thank you. And then, of course, thank to all of our 1869 Circle partners. So here's a variety of companies and firms. I won't mention them all, but take a brief moment to thank them as well. So if you'd like to, stay connected with us and continue to attend these, we have QR code you can scan. We also do publish these presentations and they get posted to our YouTube channel. So you can always check out the content there. And then our next event's similar. We'll post all this information. You can scan with the QR code and then register to attend these events and make sure you're checking the AIA website for upcoming events where you can register and attend. We have an amazing series of events set up to occur on the same time. So these first Fridays, we also have some upcoming tours and in-person gatherings that we're coordinating scheduling. So look forward to all those coming throughout the entirety of this year. And from our group ourselves, I am the programs chair and supporting role for David, our co-chair, David Swain, Kelly Moynihan, and our AI Chicago president now, and Daniel Giaconetti. So pleasure to be involved with all these group of individuals. And that's it for me. I'll stop sharing and pass it over to Dr. Alba to introduce herself and looking forward to this presentation. Dr. Alba, you are on mute.
Okay. Thank you. Thank you,
Good.
Gabriel. Thank you for giving me the word and let me share. Okay.
I can see the
So
screen. Great.
that's great. Thank you. Thank you first to all for being here. Today, I want to talk about something we all work with every day, but we rarely treat as a system in its own right, sunlight. So it's not just sunlight as heat to mitigate or glare to control, but sunlight as a shared civic resource, something that architecture can shape, distribute, and use to support life, human and non-human, in cities. Before I continue, I'd like to briefly share my academic and professional background so you can understand how it connects to the rest of this talk. I was trained as an architect in Madrid and later completed a master's degree in agricultural and biosystems engineering, followed by a PhD in architecture and sustainable design in Singapore. Alongside academia, I've built a professional career spanning over 15 years, working across the US, Europe, and the Middle East, and leading high performance projects, including a 15-story mixed use building with heat pump systems. Today, I work as an independent consultant in Chicago, collaborating with the Polytechnic University of Madrid on green infrastructure and climate responsive design. I share this background to explain the lens behind today's work. This research that I'm going to show today is grounded in practice and focus on how architecture can transform urban surfaces into productive ecological systems in support of the 2030 climate goals. Before I move forward, I'd like to briefly explain how this talk is structured and what I hope you'll take away from it. This presentation moves across research, practice, and policy. So I want to give you a clear roadmap from the beginning. First, awareness. Seeing sunlight not just as something we regulate, but as a shared resource that architecture actively distributes. Second, design intelligence, understanding how environmental data, biological performance, and spatial design can work together early in the process to guide architectural decisions. And third, agency, living with a clearer sense of what architects can do in practice to connect climate goals, green systems, and equity through design. These three ideas will guide everything that follows. To reach these goals, the talk unfolds in four main parts. First, I'll frame the problem, why food, climate, and sunlight matter for architecture today. Second, I'll introduce the research gap and the tool I developed to address it. Third, I'll show how this framework works across buildings, districts, and climates, including how it reveals issues of environmental inequality. And finally, I'll connect all of this back to professional practice and the 2030 commitment. As we move through these sections, I'll keep returning to the same questions. What does this mean for design? What does this enable in practice? And who benefits from these decisions? My hope is that by the end, you won't just have seen a research project, you'll have a way of thinking about sunlight, green infrastructure, and performance as interconnected architectural systems. With that roadmap in mind, let's begin with why sunlight matters now. We are living in a moment of planetary urbanization. Cities concentrate people, energy use, emissions, and vulnerability, but they also concentrate opportunity. If we are serious about climate positive design, cities can just be places where we reduce damage. They need to become places where buildings actively contribute to ecological and social systems. Food is one of the least discussed drivers of climate change in architecture, yet it's one of the most impactful. Globally, food systems are responsible for enormous land use, deforestation, water consumption, and emissions. At the same time, we are expected to increase food production by roughly 50% by 2030. And yet, most of this production remains spatially disconnected from the cities that consume it. When we look at cities, we see roofs, facades, setbacks, courtyards, thousands of square meters of sun-exposed surface. But we rarely ask what these surfaces could do. We treat them as passive elements when they could be productive ecological and civic assets. This connects back to our first goal, building awareness of how environmental resources like sunlight are distributed through design decisions. Much of sustainable design has a focus on efficiency, doing less harm. But what if we ask a different question? What if buildings don't just consume less, but actually produce value? Food, biodiversity, microclimate regulation, while making those systems visible and shared. Interdisciplinarity can shape how we see buildings. I realize that architects are very good at shaping space and form, while agriculture is very good at optimizing biological performance. But the two rarely talk to each other. The central question I'll focus on today is simple. How can architectural design redistribute sunlight to support crops, ecosystems, and communities while reducing energy demand? To answer that, we first need to understand the landscape we are working in. If urban agriculture matters historically, environmentally, and socially, the next question becomes not whether it belongs in cities, but how and where it is actually taking shape today. So, where is the urban agriculture revolution happening? Not in a single geography and not at a single scale, but across very different urban, climatic, and cultural contexts. What's interesting is that despite these differences, similar spatial strategies keep emerging. Across global cities, North American contexts, and practice-led architectural work, urban agriculture tends to occupy leftover, hybrid, or reimagined spaces. These are rooftops, facades, setbacks, courtyards, adaptive reuse buildings, and infrastructural landscapes. Spaces that were not traditionally considered productive, but are now being reevaluated as part of the urban system. This condition appears consistently in the literature and in built work worldwide. Globally, we see agriculture increasingly framed as urban infrastructure rather than a separate land use. In dense Asian and equatorial cities, agricultural spaces are often integrated to provide not only food, but thermal comfort, social relief, and ecological buffering. Agriculture becomes a spatial mediator between density and livability, between climate and everyday life. These projects highlight that food production is rarely the only objective. Environmental and social performance are equally central. If we shift to a North American context, and particularly to Chicago, we see a different but related pattern. Here, urban agriculture often emerges at the intersection of post-industrial landscapes, food access, and climate adaptation. Vacant land, flat roofs, and reduced industrial buildings become opportunities for food production. Chicago's climate adds another layer. Long winters, strong seasonality, and light scarcity push agriculture indoors for part of the year, while summer abundance supports rooftop and ground-based systems. What's important is that these projects are rarely isolated. They respond simultaneously to food systems, building performance, and urban transformation. This is where architectural practice becomes critical. Agriculture is not treated as an add-on, but as something architecturally crafted into buildings, landscapes, and communities. Projects such as schools with working farms, agricultural education centers, and even experimental rooftop cultivation shows how architecture can mediate between ecological systems and everyday use. What's consistent across this work is a focus on sections, surface, and performance, using architecture to choreograph sunlight, soil, water, and occupation over time. When we step back, patterns become clear. Whether we look globally, locally in Chicago, or within architectural practice, urban agriculture consistently occupies architectural surfaces and systems, roofs, facades, interiors, and hybrid spaces. But these projects are still largely case-specific. They rely on bespoke decisions, intuition, or operational constraints rather than systematic environmental evaluation. And this is where scale becomes a challenge. As these systems scale up, outdoor and hybrid agricultural strategies began to encounter limits. Climate variability, seasonal light availability, extreme weather, and pests introduce uncertainty. Yields become harder to predict, and performance becomes inconsistent across times and location. In response, many cities turn toward controlled environment, not because they reject architecture, but because they offer reliability. So while urban agriculture can exist at every scale, from citywide systems to individual buildings and homes, the pressures of reliability, efficiency, and year-round production help explain why so much of it is now moving indoors. This shift brings us directly to the rise of controlled environment agriculture. These systems are incredibly productive. They use far less water, avoid pesticides, and operate year-round. But they are also extremely energy intensive. In most cases, artificial lighting is the single largest contributor to their carbon footprint. So the question becomes, do we accept urban agriculture as a black box energy hungry system, or can we rethink it as an architectural system, one that uses form, orientation, and materiality to work with sunlight instead of replacing it? Here's where things get interesting. Plants don't use all sunlight. They only use a specific portion called photosynthetically active radiation, or PAR. This distinction is critical. Yet, most architectural solar tools don't calculate PAR at all. They evaluate comfort or energy, but not biological productivity. That means as architects, we are often designing blind. At the beginning of my PhD, I reviewed both academic research and professional practice on urban and building integrated agriculture. What became clear is that most studies focus on where agriculture can be placed, rather than whether those spaces are environmentally suitable. Three gaps stood out. Energy efficiency is often secondary. Available space is prioritized over viable space. And crop-specific light requirements are rarely integrated into design. This revealed the need for a sunlight-informed approach that connects urban geometry, environmental performance, and biology early in the design process. Agricultural models are great at optimizing crops, but they ignore urban geometry. Architectural models understand cities, but not plant biology. This disconnection limits what architects can see and therefore what we can design. Building on that gap, my PhD thesis takes a deliberately hybrid approach. It brings together procedures traditionally used in architecture and in agriculture to support green-centered environmental performance in the built environment. From architecture, it draws sunlight-informed design methods capable of analyzing three-dimensional urban geometry. From agriculture, it brings an understanding of how solar radiation affects plant growth, specifically through photosynthetically active radiation. By combining these two perspectives, the work creates a shared framework where architectural form and biological performance can be evaluated together. This allows decisions to be informed not only by spatial or energetic criteria, but also by the environmental requirements of living systems. Eliantus is a computational framework I developed to bridge that gap. It maps photosynthetically active radiation across three-dimensional urban surfaces and matches it with the specific light requirements of crops or ornamental plants. It's not about optimization, it's about expanding architectural vision. This is where design intelligence becomes operational, where environmental data becomes something architects can actually work with. Space in contemporary cities is increasingly limited and primarily allocated to urban development. For much of the 20th century, agricultural systems were systematically excluded from urban planning and management, treated as incompatible with city life. Today, that assumption no longer holds. Governments, policymakers, and urban planners are increasingly recognizing the need to reintegrate food systems into urban environments as part of broader climate resilience and equity strategies. Current research highlights a clear need for new planning tools and computational models that can support this integration. Tools capable of evaluating environmental performance and spatial suitability simultaneously. The framework presented in this work responds directly to that need, offering a sunlight-informed approach to embedding green systems within the urban fabric. To respond to these challenges, a range of existing tools and workflows were analyzed in order to understand how advanced computational methods are currently supporting high-performance design. Within this landscape, visual programming environments, such as Grasshopper for Rhino, emerge as a particularly effective platforms for research-driven design workflows. These parametric approaches allow multiple variables to be evaluated simultaneously, enabling designers to explore performance, trade-offs, and generate quantitative feedbacks early in the design process. One of the most significant strengths of parametric tools lies in their ability to support environmental analysis. This capability forms the foundation of the work presented here, where computational methods are used not to automate form, but to inform architectural decision-making through environmental performance. Parametric workflows are often associated with efficiency, using data to improve performance and reduce resource consumption. In the case of Eliantus, this logic is applied specifically to light efficiency in urban agriculture through the modeling of photosynthetically active radiation. The primary objective of the framework is to identify which plant species are environmentally suitable for specific urban conditions based on available light. Rather than treating all green surfaces equally, it evaluates performance at the level of biological requirements. To achieve this, Eliantus integrates a complex analytical methodology into a simplified user-friendly workflow. Implemented as a Grasshopper plugin, it enables detailed light-informed analysis of urban surfaces and translates that data into customized interactive visualizations that support informed decisions for green infrastructure planning and architectural design. The current version of Eliantus is organized into three main workflows: data import, data analysis, and data visualization, comprising a total of 10 components. Here, you can see the plugin integrated within the Grasshopper environment, along with a close-up of its tool menu. The complete Eliantus codebase contains a level of complexity that had to be developed in collaboration with a software engineer. The GenDyMatrix function is the core computational method used to calculate and analyze both direct and diffuse photosynthetically active radiation. The computational model evaluates key performance indicators for urban agriculture, including site suitability, crop suitability, potential yield, and overall light efficiency. Before moving into how this tool performs across scales, I want to pause briefly on an essential question. How do we know this system is reliable? For Eliantus to be useful in practice, its outputs cannot be speculative. They need to be grounded in measurable environmental reality. Sustainability-driven design depends on trust in data. If we are making decisions about form, orientation, and green infrastructure based on simulations, those simulations must reflect real environmental behavior. For this reason, empirical validation was built into the research process from the beginning. Environmental sunlight in this framework is computed through a dedicated simulator and benchmarked with on-site sensing. Physical sensors recorded photosynthetically active radiation under real conditions, generating over 6,000 measurements across multiple locations and time periods. These data were compared with simulations derived from calibrated climatic databases, showing strong agreement between measured and predicted values. This validation establishes a reliable link between physical conditions and digital representation, making the tool trustworthy for design decision-making. What matters is not only that the simulation works, but what it enables in practice. It allows architects to work with data grounded in real environmental behavior, not abstract predictions. This highlights the value of empirical data as a design tool. Sensors help benchmark models early, verify assumptions, and compare predicted and actual performance, creating a feedback loop with the digital twin. For green infrastructure and building integrated agriculture, this reliability is essential. With this validation in place, we can now move into how the framework performs across scales. With this framework, designers can evaluate where agriculture makes sense, what can grow there, and how early design decisions like massing or facade articulation change performance. This happens early, when design intelligence matters most. Sunlight doesn't stop at the building line. This is what design intelligence looks like in practice: the ability to translate environmental data into spatial decisions across scales. The same logic applies at the scale of a facade, a campus, a district, or an entire city. This makes sunlight a powerful connector between architecture and urbanism. Thinking across scales also means thinking across climates and across seasons. To test the robustness of this approach, the framework was applied to case studies in cities with very different climatic conditions, many of them in rapidly urbanizing contexts. By analyzing photosynthetically active radiation in places such as Mexico City, Lima, Cape Town, Muscat, New Delhi, and Jakarta, the work explores how sunlight from design responds to diverse environmental constraints rather than relying on a single climatic model. This comparison reveals that sustainability cannot be treated as a static condition. Urban agriculture and green infrastructure must perform not only in a typical day, but across entire annual cycles of light, temperature, rainfall, and seasonal variability. In some climates, summer becomes the critical period for heat stress and water management. In others, winter light scarcity defines what is possible. What counts as sustainable in one season may be inadequate in another. This reinforces the idea that environmental performance is always contextual and that design intelligence must be adaptable to climate, latitude, and local conditions over time, not just in space. In other words, thinking across climates means designing for seasonal sustainability, where strategies evolve with yearly changes rather than assuming constant conditions. Again, this reinforces our first goal, understanding that environmental performance is always contextual and never universal. At the building scale, this approach shows how envelope thickness, orientation, and material transparency directly affect crop viability and energy demand. Form is no longer neutral, it becomes performative. At the district scale, the tool reveals something else: solar inequality. I want to frame this district scale study through a social lens. In cities, sunlight is not distributed equally. Building height, orientation, and density determine who receives daylight and who lives in shade, producing what we can call solar inequality. These environmental differences often overlap with social and economic disparities, limiting access to green and productive spaces. In this sense, sunlight is not only an environmental resource, it is a social one. Understanding its distribution is essential if green infrastructure is to support equity rather than reinforce existing inequalities. Some surfaces receive abundant light. Others are permanently shaded. Design can redistribute this resource more equitably if we choose to see it. This is exactly what I meant earlier by awareness. Once we can see how sunlight is unevenly distributed, we can no longer treat it as neutral. At the city scale, this becomes a planning question. Where could networks of productive roofs exist? Where does agriculture strengthen resilience instead of competing with other uses? This reframes architecture as civic infrastructure, not just housing people, but supporting food access, ecology, and public life. Buildings become mediators between environmental systems and everyday experience. This work isn't about putting greenery everywhere. It's about design intelligence, knowing where interventions make sense and designing them intentionally as part of a larger system. Sunlight informed design supports carbon reduction, resilience, and equity. It also makes performance visible, which is essential if we want climate goals to shape design culture, not just reporting metrics. Looking ahead, this framework can integrate food with water, biodiversity, and material flows, expanding architecture's role in regenerative urban systems. As architects, we shape how environmental resources are distributed. Sunlight is one of the most powerful and most overlooked. Designing with it intentionally allows buildings to actively support life, not just shelter it. Before I close, I want to connect this work to the AIA 2030 commitment. The commitment calls on architects to move toward net zero emissions by placing environmental performance at the center of early design decisions. The Sunlight Framework supports this shift by expanding performance beyond energy to include living systems and ecology as part of a broader green infrastructure agenda. Here, green infrastructure is understood as a strategic network that delivers ecological, social, and climate value across scales. By integrating this approach into design, architects can translate the 2030 goals into form-driven decisions that not only reduce impact, but actively regenerate urban environments. In this peer-reviewed research, we define green infrastructure not as a single element, but as a strategically planned system, a network that delivers ecological, social, and climate performance across scales. One of the key findings is that green infrastructure can contribute to all 17 Sustainable Development Goals, with particularly strong impact on sustainable cities, climate action, ecosystems, and food security. This positions green infrastructure as one of the most effective spatial strategies for advancing the 2030 agenda. What the sunlight-based framework adds is design specificity. It allows us to quantify how architectural form enables or limits ecological performance. Through this lens, we see clear alignments across scales, from building envelopes that mediate light and growth to districts that redistribute environmental resources and cities where green infrastructure supports resilience and climate adaptation. Many awarded and widely recognized projects already demonstrate this thinking, often intuitively. What these works contribute is a framework that makes those relationships visible early in design, allowing architects to intentionally align form, performance, and the objectives of the 2030 commitment. This is where awareness and intelligence begin to turn into agency, into real architectural choices. In that sense, sunlight informed design becomes a practical bridge between research, architecture, and climate action, helping translate global goals into spatial architectural decisions. As architects, we have the opportunity to design green infrastructure as part of architecture itself, creating human-made biosystems that actively regenerate the natural systems we depend on. But this requires interdisciplinarity inside practice. Climate, ecology, and green systems are not isolated problems, and they cannot be addressed through architecture alone. They demand designers who can connect disciplines, translate data into form, and work across scales. This is where awareness, design intelligence, and agency come together in how we structure teams, tools, and design processes. Interdisciplinarity and interdisciplinary architects play a critical role in that shift, helping studios move from isolated performance metrics to integrated regenerative design strategies. So I hope that this work sparks new conversations about how research, tools, and practice can come together to create truly climate positive cities. Um, I am very happy to continue now the conversation. Thank you.
Thank you, Dr. Alba. It was great. Appreciate the
Thank you.
presentation. And I would open it up to the group. If you have a question, please, you can unmute, ask the question, or put your question in the chat. I do see one question here from Thomas Boyster. Question is, how does this overlap with photovoltaics or solar cells? Do these approaches to green infrastructure overlap, such as building integrated PVs, canopy with growth below, or each occupy their own preferred conditions?
Thanks. That's interesting. Yeah, actually, it really overlaps since I mean a big part of the study is to analyze how the building envelope affects the light within these productive or green spaces. And of course, PVs are like the fact that there's advancements in research into transparent and translucent PVs. It's been very interesting as a nexus with these two areas of research. Yeah.
And I
Thank you.
see a very important question on there as well, asking where can we get the Helanthus plugin?
Yeah, so the Liantos plugin, actually, the code was developed as an open source Grasshopper plugin as part of my PhD thesis research, and this is in GitHub. But the intention of the plugin is to keep developing it towards more practice-oriented workflows, so it can integrate more easily into specific architectural design processes. Because at the end, every firm and every studio has its own ways, and it's always better to try to rebuild it all towards a specific frameworks. But yeah, it's open in GitHub as well, but just the code.
I'm
And then I see,
wondering,
go ahead.
one of the things that really struck me was the empty building that you showed in Chicago and the potential for
Yeah.
it to be a food hub, energy use being one item to consider, but so many empty buildings. And, people just think of the traditional, how do you rent this space out rather than how does it become a resource? That really got the wheels churning. I'm very interested in seeing, is there an application for the program that you have for things that already exist now, like these empty buildings, and how to actually propose these to the people that are making decisions to kind of, serve it up on a silver platter so that it makes it a lot easier to make a good choice.
Yes, thanks. I agree. Safiro is like that's very interesting. I actually was excited when last month I think I suddenly see this example that is going to happen soon in the city. And it was very interesting to see how this private investor, Mark Calabria, is interesting or saw the opportunity of doing this because, of course, I mean, to feed the increasing population and to stop reducing forests through we tend to change agriculture forests for agriculture to be able to feed the whole population, and then we end up not having any forest or any natural environment, and it doesn't have any sense to have production and consumption away. So this is a very exciting project that is going to happen soon in Chicago, and yes, there's so many vacant spaces that it is a very exciting project that is happening here in this city.
The other thing that I would say about the felling of forest tree to turn into agriculture, I think a bigger concern is how agriculture actually produces food. There's a huge concern about the monoculture and what that actually is. That actually effective? Is it the most effective use of land? And there's a lot of argument saying that it is probably the worst way to produce food. So we could probably shore up that system tremendously, both for the health of the planet and just to increase the numbers more appropriately for food production.
Yes, that's why, like at the end, regenerative agriculture and permaculture is moving. These are concepts that exist since the 1970s, but are moving agricultural land into more sustainable production systems that instead of, as you said, produce on monocultures, they are solid ecosystems that have a mix of greenery and a mix of also not just plants but also animals that build a strong ecosystem that not just produces food but is food that is free of any chemicals, because actually the monoculture agriculture is really bad not just for the environment but for humans as well. And that's the exciting part of starting to mix agriculture within urban centers, that we have the opportunity to have hybrid spaces, like literally every building could have a little farm in a rooftop or a facade, and it's pretty easy to integrate with our actual urban environment, even in existing buildings. And the nice thing about indoor environment against outdoor is that it's more control, and it allows us in indoor environments actually you can be monoculture because you are not damaging the actual environment, you are in an artificial one, and it becomes important also to be able to reliably feed the whole population, because you cannot get rid of one system that is producing very high yields without having another option that is as much yield, highly yield than the one that we have in place right now.
And one last comment. I've met a
Yes.
few people that are in the industry of creating rooftop greenhouses. So in Chicago, with all our flat roofs, that just would seem to be an excellent coupling with our roofscape.
Yeah, that is very exciting, and one thing that is because somehow it's also exciting that it's related to architectural form, and the most interesting part is that it makes actually the form of buildings performative, and how massing and envelope articulation and section start to influence, or these or flat rooftops start to influence ecological productivity, not just energy. And that opens a new layer of architectural decision making. And that's very exciting.
Great. Any other questions from the group? We have time for about two more.
I have a second different one. Are you familiar with any examples of controlled environment permaculture approaches? Typically, I see them separated, like you're describing with monoculture and controlled environment. And then I guess it's not permaculture if it's not permanent because it's controlled, but that sort of gilding ecosystem approach.
Thank you, Thomas. It's kind of separated because permaculture tries to generate strong, like natural, more natural biological systems outdoors. So it engages with animals and with insects, and it generates biodiversity. And also it is very important for the soil, because we are damaging soil a lot through the regular type of agriculture. So that engages towards that. And when we go to indoors, the fact is like we want to optimize production and to produce as much as possible. In this case, for example, the tool allowed you to manage like a seasonality, and maybe not in the mix even crops. Like for example, in a facade, you will have maybe higher levels of sunlight on the top than on the bottom of a skyscraper, because actually I measure it with sensors, and there's higher levels on the top floors than on the lower ones. And that gives opportunity to maybe do like a mosaic where you mix species, but they are not acting as an ecosystem. You are just trying to produce as much as possible to feed as much people as possible. But it is exciting. The thing that is similar and it's exciting about both is that they don't need chemicals to produce high quality crops, which is very interesting for us as humans, because then we don't eat things that are actually not good for us.
Thank you.
Thank you.
Great. Well, we are at time, and I really appreciated it, Dr. Alba. So the open source you're referring to is the code that you've created that anyone could
Yeah.
copy and create into Grasshopper.
Yeah.
Great. Thank you. Appreciate it.
Thank you so much. Thank you. Thank you for your attention. Thanks, Gabriel. Thanks.
Thank you.